question. And also no more raised hands. So I would say I would like to thank you again for your talk. And then we move on to the next talk, which is also somehow related to binaries, and which will be given by Nicolay Walters. So could you please share your screen?
Yep, 1 second. Hiya. Hello to everybody. Well, my name is Nicolay Walters. I'm a UCL student, and today I'm going to talk about the project that I did for my PhD. So this talk is mainly based on a recently published paper with the same title. So if you'd like to perhaps follow up this presentation, then that paper would be a good place to start. Anyway, some of my collaborators on this work include Jay Farihi, Tom Marsh, Stefano Bagnulla, John Landstreet, JJ Hermes, and Nick Achilles. To begin with, I'll give a brief introduction to magnetic white dwarfs, and then the primary target of this investigation. And then I'll introduce the unipolar inductor model. So magnetic white dwarfs are relatively common. About 20% of white dwarfs have detectable magnetic fields. Although magnetism is frequent, the field formation mechanism in degenerate stars is still unresolved and remains a fundamental problem in stellar astrophysics. The effects of magnetism on stellar evolution also remains unclear. So let us look at field distribution. So as can be seen, field strengths range from a few kilogauss and up to 1000 megagauss. Typically, magnetic white dwarfs are identified spectroscopically, or in some cases via spectropolarimetry. Figure on the right shows the effect of magnetism on H-alpha absorption line with increasing field strength from top to bottom. This Zeeman effect is visually evident in H-alpha core splitting into multiple features, which are then displaced from the unperturbed position. Returning to field formation mechanisms, there are two major theories, starting with the fossil field idea. A single main sequence magnetic progenitor basically evolves into a magnetic white dwarf. Such a progenitor could be A or B peculiar star and can have field strengths ranging from about a kilogauss to a tenth of a megagauss, as shown in this histogram, of volume limited A and B peculiar stars. In a slightly alternative scenario, magnetic field could be hidden in progenitor star's core. But either way, the relatively modest magnetic field of the progenitor then gets amplified during its evolution into a white dwarf. Second hypothesis requires a companion that helps produce a dynamo. So for example, during a common envelope episode, spiral in of the secondary could induce differential rotation in a convective envelope, this resulting in a stellar dynamo. Such binary evolution mechanism could explain why, for example, magnetic white dwarfs are, on average, are a bit more massive than typical DA counterparts. Well, now that we know some field formation mechanisms, it will be useful to also know some, to know what observable effects magnetic field could have on a white dwarf. And one of the more common effects would be, in my opinion, photometrically inferred spots caused by surface inhomogeneities or by a lack of atmospheric convection due to field inhibition. There could also be effects on accretion in binary systems, convective mixing, non-uniform chemical surface composition, and continuum flux and photometric modulation. One thing I want to focus on a bit more is the effect of non-uniform magnetic field on observed spectra. During a rotation, a hypothetical white dwarf would show different field geometries, resulting in spectroscopic changes. So just to give a concrete example, what shown here is a trail spectrogram of H-alpha feature of a magnetic white dwarf G183-35. And the dark regions represent lower flux values. So you can see the side components of the triple kind of varying in wavelength. Okay, so here is the primary target of this investigation, a magnetic white dwarf GD356. It is a relatively cool white dwarf with effective temperature comparable to the sun. It's optically variable with a peak-to-peak amplitude of 0.4% in the V band, indicating that it probably has as a spot on its surface. By itself, this is not very remarkable because, as I mentioned in the previous slide, the presence of spots is a common phenomenon for magnetic white dwarfs. Yet GD356 remained unique out of over 25,000 spectroscopically observed white dwarfs up to early 2020s. And the exotic thing about this star is its optical spectrum. So it's an interesting one, but what's evident is that we don't see any absorption features intrinsic to the star. Instead, there are Zeeman split emission triplets of H alpha, H beta, and a single H gamma feature. It's not obvious what mechanism can be causing this emission. It's a relatively cool white dwarf, so the emission cannot arise from the photosphere. It must be due to a temperature inverted region. However, when it comes to conventional heating mechanisms, they've all been rolled out. A deep Chandra pointing established X-ray luminosity constraint. So when compared to emission luminosity, the X-ray constraint falls short by a factor of 100. Thus, we can rule out a stellar corona as the source of emission. Secondly, cryogenic Spitzer observations found no evidence for infrared emission beyond the photosphere. This rules out accretion from the interstellar medium and a substellar mass donor down to about 12 Jupiter masses. Since the conventional heating mechanism are kind of inapplicable in this case, an external heating mechanism called the unipolar inductor was proposed for this system. So generally speaking, the unipolar inductor model is not specific to white dwarfs, but it's a type of interaction that could be applied to any strongly magnetic body and its companion. The basic idea is that you have a primary with a magnetosphere and a secondary companion with high internal conductivity within this magnetosphere. Due to the magnetic effects, a current loop could form between the primary and the secondary, but the loop would be incomplete in this case. So as an example, Jupiter Io system marginally fits this description, with Io creating a noticeable footprint or spot on Jupiter's surface as Io orbits around. So this current loop that connects the two would be dynamic, and the position of its endpoints where it reaches Jupiter's surface forming the footprint would depend on the position of its companion. And now in the context of white dwarfs, similarly, for the model to work, you would need a magnetic white dwarf and a conducting or rocky exoplanet. Again, in such a system, the current loop would be incomplete unless you get energy dissipation via ohmic heating on the white dwarf's photosphere, resulting in two hotspots. Put simply, we would have a very inefficient circuit that creates temperature inverted regions where the current is stopped. Such white dwarf planetary interaction was first proposed to explain the spectroscopic features of GD356. So the applicability of this model on GD356 was the primary motivation behind this work. And when testing a model, I mean, it's usually good to know what are the model predictions. And the unipolar inductor makes several testable predictions, but I want to focus on just one for now. Namely, the relative position of the heated regions would vary depending not only on the white dwarf's dynamics, but would also be modulated to some degree by the companion's orbit, as you can hopefully see from the graphic here. So put very simply, we would expect additional signals beyond white dwarf rotation. And to test this idea, we took some time-resolved optical spectroscopy of GD356 on William Herschel telescope. So what you're seeing here is a trail spectrogram of H alpha and H beta triplets of GD356, different rotational phases. So x-axis represent wavelength and y-axis show the rotational phase. Brighter yellow colors correspond to higher relative flux values. At the bottom, I also included an example of a spectrum, just for reference. And okay, so first, we see the intensity variation in the emission. And secondly, I can't show it with my mouse, but there is a notable change in the emission central wavelengths for some of the components. This can be seen as a sinusoidal pattern, for example, at about 6,300 angstroms. Hopefully you can see that. And to quantify emission strength, we could measure equivalent widths, which are shown in the top panel. And these were phase folded on a 2-hour rotational period. And to measure shifts in central wavelengths, we could fit the emission features themselves, and then use the fit parameters as a proxy. For example, fit the emission with the Gaussians, and then the means as a representation. So these are, of course, I have to say, these are not radio velocities, radio velocity changes, but rather the effects of GD356 magnetic field. So the field is non-uniform, and thus we see the features drifting based on a viewed magnetic field geometry. Additionally to the spectra, we also analyzed photometric data from multiple telescopes. Shown here is photometry from TESS and the Liverpool telescope. The 2-hour period is recoverable, and the signals approximated quite well by a sine model. This sinusoidal variability was first presented in literature almost 20 years ago, so the source of variability is likely stable on this timescale. Additionally, kind of passing the photometric data from TESS to Alom's cargo periodogram algorithm shows that the period is quite well constrained. Running the same algorithm on the equivalent width estimates also recovers the same period, albeit slightly less constrained. Nonetheless, the point here is that the period is so well constrained that we can meaningfully compare photometric and spectroscopic data. Another thing to note is that there are no strong secondary signals. If the variability is caused by a hotspot, then this observation is inconsistent with the prediction made by the unipolar inductor model. Fourthly, and rather surprisingly, we see that the photometric maximum corresponds exactly to emission strength minimum. In other words, they are exactly out of phase. In the context of the unipolar inductor, we would expect a hotspot to be the source of the emission, but the data points at a dark spot as a potential source. This, however, could hold some similarities to sunspots that appear opaque in optical but bright in UV. Currently, GD356 variability in the ultraviolet is unknown. And finally, I just want to emphasize that this anti-phase relationship is not accidental, even though the spectroscopic and photometric data were taken almost 2 years apart. Our photometric analysis also confirmed that this variability is consistent with a single fixed period model. While analyzing this data, 3 further isolated white dwarfs with similar emission behavior were identified. And these are J1252 on the left by Redding et al., J1219 on the top right by Gansiki et al., and J0412 on the bottom right by Tremblay et al., all reported in 2020. J1252 and J1219 are known to be magnetic, while J0412 magnetic properties are unknown. There are currently no time series spectroscopy of J0412, but so far it appears to belong to the same DA emitting class. The position on the HR diagram is also of interest. So here is GD356 on the white dwarf cooling sequence from Gaia. And here are the other 3 emitting white dwarfs. Hopefully you can see that such close clustering is very unlikely to be accidental. If emission in these stars is indeed triggered by an external process, such as the unipolar inductor, it's not clear why it only appears to be active at a certain evolutionary stage. Instead, the distribution strongly suggests that the emission mechanism must be internal and likely intrinsically activated at a specific stage. Moreover, there are multiple properties shared by these four objects, other than having hydrogen emission and similar luminosities. For all four, the rotation rates are relatively fast compared to the typical white dwarf rotation. In fact, J1252 is the fastest rotating, apparently isolated white dwarf. Also, for this rotation rates to be photometrically detectable, would require some kind of a surface inhomogeneity, suggesting that these stars are likely have similar dark spots. Finally, at least 3 of these objects are highly magnetic, potentially pointing that magnetism might be responsible for the emission behavior. And I just have to know that J0412 was not studied for magnetism, so whether it's magnetic is currently unknown. So this raises a number of issues when it comes to applicability of the unipolar inductor system. I already mentioned the antiphase relationship between photometry and emission strength and the lack of secondary signals. To add, the rotational rates of these white dwarfs also limit the effectiveness of the unipolar inductor energy transport due to extreme differential rotation of the star with respect to any planetary orbit, causing a notable centrifugal force on ions. And lastly, the close clustering on the HR diagram also does not favor an external mechanism. In this context, an internal heating mechanism seems more likely, such as an intrinsically activated chromosphere with potential dependence on rotation, magnetism, and temperature or luminosity. However, we don't have a lot of constraints on the physics of such an active chromosphere in degenerate stars, and we also don't know the nature of the surface heating mechanism. On the other hand, we can make some predictions. If it is chromospheric activity, we would expect to see only species consistent with the stellar atmosphere in the emission. And since we are only seeing hydrogen emission, we can then also predict that all 4 emitting stars have hydrogen-rich atmospheres. And kind of going beyond this idea of chromosphere, in this internal heating picture, a number of additional predictions can be made, and these 4 white dwarfs united into a single class with shared properties. So based on this, we would expect the J0412 to also exhibit a similar emission variability and a detectable magnetic field. More likely, further search of this region of the HR diagram will also source additional candidates. Lastly, I just want to say that ruling out unipolar inductor does not mean that this emitting stars are probably no longer good candidates to search for signatures of exoplanets photometrically. And just to summarize, we believe the unipolar inductor model provides a poor fit for GD356 and the further 3 isolated white dwarfs with Balmer emission. Instead, we think that these white dwarfs form a distinct evolutionary class with emission produced by an active chromosphere triggered intrinsically at a specific evolutionary stage. And that's all I wanted to say. So thank you for listening.
Yep. So thank you very much for your talk. I cannot see a question yet. So maybe I asked one. Did you check against magnetic white dwarfs which are lying in the same region in the Hertzsprung-Russell diagram if they showed a similar kind of behavior? Or are there simply not many other magnetic white dwarfs?
So the distribution of magnetic white dwarfs on the HR diagram, I would say they're definitely not clustered in that region. I would say a bit more. They're quite well separated. So you see magnetic white dwarfs throughout this sequence, this cooling sequence. But there are, I believe, some cutoffs at extremely hot temperatures where we don't see any. But yeah, this is definitely not the case that all magnetic white dwarfs lie in that region.
No, I meant if the magnetic white dwarfs which lie in this region do show, if there are other magnetic white dwarfs in that region, if they all show this behavior?
Well, when it comes to this emitting behavior, I haven't seen any because obviously you need a spectroscopy to actually identify these emission features. But and this is how magnetic white dwarfs are identified via spectroscopy. So I would imagine if there is a spectroscopic kind of a detection of magnetism, then the presence of emission would also be quite obvious.
Okay. There was a raised hand by Klaus Werner, but it's not raised anymore. So if you want to ask something, just speak up.
Yes, please. Nicolay, are there any dB white dwarfs showing this emission line phenomenon?
I'm not familiar with any dB white dwarfs that show that, but I know there are some metally white dwarfs with metal pollution that shows emission, metal emission.
Yeah. Okay, thanks.
Okay, then the next question is, you said that if caused by intrinsic chromospheric activity, that these emission features would represent the dominant element in the white dwarf atmosphere, which would be hydrogen in the emission cases. However, Bergeron et al. Found that the SED of GD356 fits best with a helium atmosphere models. Do you have any thoughts on this mismatch?
Yeah, so I just want to mention that fitting magnetic white dwarfs SEDs can be a bit more challenging than non-magnetic white dwarfs. So I think that's the case when the magnetic field kind of prohibits a good fitting. And so I do not believe that GD356 got a helium-rich atmosphere. I think that's just the case that it wasn't the magnetic effects were not accounted for properly when fitting, and I don't think it's a straightforward thing to do to account for such effects.
Okay, then the next question is if you do plan to obtain time-resolved spectropolarimetry.
We actually already have some time-resolved spectropolarimetry of GD356, and again, the analysis of that is presented in the paper. But I guess if you have a specific question, I could answer it. But if not, then the paper would be probably the best place to look.
Okay. Then there's a comment from Pierre Manuel. He comments that our data on J0412 shows Balmer emission varies on 2.5 hours and the rotation period consistent with a spot.
Okay.
And then, since your talk was quite short, we have time for another question, which is by Stuart, which he says, sorry, it's a long one. So as well as the LO footprint, IO footprint, Jupiter also has a main auroral oval, which originates from a breakdown in co-rotation between the magnetic field and the plasma in the magnetosphere. All you need for this mechanism to work in the white dwarfs is a strong magnetic field and some ionized plasma in the white dwarf's magnetosphere. This plasma may come from, for example, a remnant debris disks. Perhaps it could also explain the clustering if the ionization radius at the given temperature coincides with the region at which the co-rotation breaks down. Have you considered such a model?
Quite frankly, no. This is the first time, but it's a very interesting one. So thank you for sharing that. Yeah.
Yeah, maybe in the coffee break you can keep on discussing this. And Then we can take one more question, which is, wouldn't a cool helium magnetic white dwarf have a near featureless spectrum? So the hydrogen emission lines could just be the contamination mentioned by Stuart?
Sorry, I'm a bit lost with the names, but contamination in what sense? What would be? I get the idea that I think I understand the question, but I'm a bit lost as to what would be causing the contamination. That would be, I guess, be the source of the emission in that case.
Well, I got the impression that you thought that the unipolar inductor model was failing, but it seems like if you had a cool helium white dwarf with practically no features, and you were connecting it then to a planet which presumably had hydrogen, you could just be inducing a hydrogen and chromospheric contamination.
Okay. Yeah, but I guess if I didn't make it clear, there are other issues with the unipolar inductor model, kind of beyond that. So, for example, just to give one, it's the rapid rotation rate. So one of these emitting white dwarfs rotates at something like 700 seconds. So that introduces all kinds of problems when you think about the connection, the loop that must be maintained. So you get this something similar in a sense to a propeller effect, where the ions just kind of struggle to kind of, I guess, form a footprint in that case. Does that at all explain it?
Maybe you can keep on discussing in the breakout, in the coffee break. And yeah, let me thank you again for your talk.
Great. Thanks.